So hey, it's super exciting to be here. I can't remember the last time I was out at one of these. It's just such a fun meetup. So my talk today, it's going to be a little bit more on the technical side. We're going to be talking about Postgres, MVCC, and U, and it all started from the question that I had one day, which is asking why count star is slow. And if those words don't make any sense to you, that's cool. I'll be giving you a bit more context in just a minute. To tell you a little bit more about myself, though, my name is David Wolliver. If you want to follow me on Twitter, I'm at Wolliver. I am primarily a Python guy. I started PyCon Canada back in 2012, and it's really exciting for me this year because we're going to be having our first PyCon Canada outside of Toronto in Montreal. So if you do Python or you're interested in Python-related things, check out pycon.ca. It's November 18th-ish, and it's going to be spectacular. In the day, I started a company called Akindi. We do Scantron-style bubble sheets. You know, when you're in school, you're filling out the multiple choice bubbles with an HB2 pencil. Well, we are revolutionizing that market. You can use HB, HB3, or even pens. Finally, this talk is still, this is going to be my second iteration of this talk. So it's still a little bit of a work in progress, so please forgive a few potential and a bit of scatteredness. Anyway, let's get started. So, just to make sure everyone's up to speed here, I'm going to be talking about transactional databases. So, what is a transactional database? What is a transaction? And what does that mean? In the context of a transactional database, a transaction encapsulates a series of operations which only make sense when they're performed together. So another way you may have heard this talked about is a series of operations where everything succeeds or everything fails, but you don't get left in the state of, say, half of the operation succeeding and half failing. The kind of canonical example of this is a bank transfer. If I'm sending you money, we're going to have to withdraw $100 from my account and then add that $100 to your account. And it doesn't make sense if, say, we withdraw that $100 and then the software crashes, and now the $100 has vanished. Another example that's a little bit closer to my heart because I deal with tests every single day is if a teacher on the Akindi system wants to go and update their answer key. That's obviously going to involve a few different steps. We have to update the answer key, we have to recalculate the student grades, and we have to then recalculate the test's average mark. Now, of course, we're all programmers, and we know that anything, with the exception of maybe the halting problem, is possible. But transactional databases make this really easy. For example, if you haven't seen SQL before, this is the programming language SQL. It's what the database, Postgres, that I'm most familiar with, uses, and it's what I'm going to be using throughout this talk. This is an example of what updating that assessment's answer key might look like. So the first line, we see it's updated. It's all bubbles, so bubbles ABC. We're going to recalculate all the students' grades, and then we're going to recalculate the assessment's average mark. The begin and end signal to the database that this is a transaction, so everything needs to happen or everything needs to fail. So, for example, if the database crashes halfway through recalculating the students' grades, we don't want even the answer key to be updated. We want everything to fail. Now, for the pedants in the room, I do want to make it clear that we can implement these transactions in databases, or implement transaction-like semantics in databases that don't natively support them. But I could talk for an hour about that, and that's not what we're here to do today. If you're curious, I've got a blog post here where I describe how you can implement an atomic bank transfer using CouchDB. And there's a bunch of other examples online. And I'll tweet all these slides afterwards, so don't worry about catching all the URLs right now. Finally, just a couple examples of databases that do and don't support transactions. So obviously, SQL databases, which is what we're going to be talking about. Interestingly, this is probably something most people don't know, so you can be a lot of fun with this trivia at parties, is that Redis does support transactions through its multi-exec commands. Neo4j also does that. And notice that there's the more kind of documented, distributed-oriented databases don't support transactions. And that's because, kind of by their nature, they're designed to scale out and to be run on a whole bunch of different machines. And it's provably impossible, your CAP theorem, that you can't support transactions in the same way in those sorts of environments. For those of you in the room who've heard of ACID, if you haven't, don't worry about it. You can Google it later or not. Your life probably isn't going to change if you don't. But you may be asking, well, aren't all databases atomic, or at least all databases worth using? The important distinction is that all databases, so like MongoDB, for instance, has a single document of atomicity. So if I send a new document into MongoDB, and if it doesn't, just lose everything, either that entire document will be updated, or nothing will be updated. Contrast that with the kind of transactional databases that I'm talking about, which support multi-statement atomicity. So in CouchDB, or in MongoDB, for instance, there's no way to say, I want to update one document, and I want to update this other document, and have both of those happen or neither of them happen. You kind of have to build your own systems on top of it to make that possible, if those are semantics that you need. So, hopefully if you haven't seen transactions before, or if this is kind of new to you, you're a little bit closer to on the same page. So we're going to get back to the question that started me down this whole rabbit hole. Why is count star slow? So count star, just for those of you who aren't as familiar with SQL, lets you count rows. And so if we say, count star from large table, what that's going to do is just count the number of records in that table. For instance, I ran this command earlier today on my production database on a table with 14 million rows, and it took a whole whopping 11 seconds. Like that's ridiculous. The whole point of a database is to perform these operations quickly. And it really got me thinking, why is that? Like, why can't we do that quickly? So if you Google around a little bit, chances are, if you're looking at Postgres, you're going to find the Postgres wiki, and it's going to tell you, the reason this is slow is related to the MVCC implementation in Postgres SQL. The fact that multiple transactions can see different areas of data means that there's no straightforward way for count star to summarize the data across the whole table. Postgres SQL must walk through all the rows in some sense. Yeah. I'm glad that was as informative for you as it was for me. Now, probably what you're thinking in your head is, well, like, a database, really, under the hood, all it is just a big tree structure, right? And surely each node can just like kind of store the count of the number of nodes underneath, then we can optimize that so that at the end of the day, to do a count star, we just need to look at that little count, like subtree count metadata on the node. Maybe if it's not there the first time we do the tree walk, but then second time it's cached, and we're all good and fast. We should be able to do that, right? I mean, aren't Postgres developers maybe just lazy? Well, surprise, it turns out no. And in fact, it turns out no on both of the statements that I made there. So, first thing, Postgres doesn't actually store its data in a tree. This could be a little bit surprising to you. Don't worry though, if you've done your database courses, it does use B-trees for indices. But when we're actually storing rows, and one of the terms that I'm going to be using interchangeably here is rows and tuples for reasons that relate to relational algebra, which is a horrendously boring thing that if you're into it, that's cool, but it's not my jam. I'm going to be using those two words interchangeably, and they both mean in this context exactly the same thing. So when we insert a row into Postgres, when we say, add a user to our users table, what's actually happening under the hood is it's just being stuck, first come, first serve, into this page structure. Pages are Postgres's abstraction that lets it group a bunch of rows together and then operate on just a collection of rows at once when it's storing them, moving them around internally, that sort of thing. And in fact, you can even see if you've got a Postgres database handy, by selecting and asking for the CTID column, you can see exactly which page and the index into that page, how far into that page each row is stored. So the second question, we were saying, well, can't we just like store the count of each node and then just like sum those counts and we're done in the quick? Well, it turns out the answer to that is also no, because the number of active rows, the number of rows that you're going to see if you run a query against the table, say you run a count star, is going to depend. And the reason it depends is the second term that I want to introduce you to, and that was in the title at the top. MVCC. MVCC stands for Multi-Version Concurrency Control. It does a few nifty things for us. The first thing that it does is if you've ever used transactions in an SQL database, you know that you can say begin, and then you can do some massive operation like deleting all the users from your system. And then you can type rollback, and it will just undo. It magically vanishes, and all the users are still there. The second really cool thing that it does for us is it means if we have two transactions, so we have the transaction on the left and the transaction on the right. If the transaction on the left goes ahead and deletes all the users from the table, but before it commits or rolls back, rollback is the operation of undoing, commit is the action of committing, right? Make these changes permanent. So if somebody else comes along and queries for the users at exactly the same time, even though, as far as the right-hand side is concerned, the users are all deleted, the left-hand side, they're all still there, and they can still see them like normal. So this is really cool. I guess this is really powerful. It makes writing correct applications in some contexts a whole lot easier. But this raises the question, like, how does this work? What's going on under the hood that makes that possible? Now, this is where we're going to dive specifically into Postgres. I'm sure MySQL and other SQL databases have their own implementations that are probably roughly similar. But Postgres is really interesting. And even if you don't use it day to day, I think it's pretty instructive and just interesting to learn how it works. So, the way this is all implemented in Postgres, it all hinges on this one magical number called the XID. XID, or transaction ID, is a number. It's just a sequentially incrementing integer that's assigned to each transaction in Postgres. So, for instance, if I start a transaction, and then I say, give me the current transaction ID, I get a really large number back. If I do it again, I'll get the next transaction ID. These are, like I mentioned, these are just sequentially incrementing integers. There's nothing special, there's nothing magical about them, except that they're ordered. The second thing is that each row, when it's stored on disk, in addition to the columns that it normally has, it also has this xmin and xmax column. The xmin is the transaction ID that created that row, and the xmax is the transaction ID that either updated or deleted that row. So, for example, if I insert a row, so I'm going to begin a transaction, I'm going to get the current transaction ID, 1, 2, 3, 4, and then insert a row. When we look at the xmin here, that's going to be the transaction that inserted the row, so our current transaction, and xmax, we haven't updated or deleted it yet, so it's just 0. Now let's take a look at what happens if we try and update that row. So again, we're going to start a transaction. We'll notice that our transaction ID is now 1 larger. And then we're going to perform that update statement. So changing the rating from 99 to 100. This is where things get a little bit surprising. You'll notice that when we look at that xmin and xmax again, instead of being 1, 2, 3, 4, like it used to be, the xmin is now 1, 2, 3, 5, the new transaction, and there's no xmax. So what happened to that old row? Well, if we roll back, so we'll undo that change, and look again. Oh, this is too low for everyone to see. We can see that the old row is still there. You notice the rating is 99 on the right-hand side. But the xmax has now been set to 5, so the transaction that updated the row. And
what's the rating?
The rating? Oh, say again?
What's the rating?
In what sense? This is a spectacular style, so they don't make any more.
So,
I think it's an arbitrary value.
Yeah. Oh, sorry. Yeah. So I see what you're saying. The rating here, I'm just using for illustrative purposes. It's just a number.
Okay.
Yeah. Yeah. Thank you for that. Clean this up in the next version of this. So now, one of the things that we could do is if we could actually here on disk and look at that database page, we would see that new row. Remember, we updated. We set the rating to 100. So we'll see that there's a new row in that page where both the xmin and xmax are 1, 2, 3, 5. Now, okay, cool. So I've given you some examples, and you're probably pretty confused right now because this has been a lot of seemingly disparate information that I've just kind of vomited at you. So what is the point? Why are we doing all this? Why am I talking about this? So the point here, and these numbers are used for deciding which rows are visible. Remember, going back to the problem of why we have to count and why the number of rows that are visible varies, is because, well, there are different visibilities. So if you remember that earlier example that I showed you, where one transaction can delete all the rows from a table, and concurrently at exactly the same time, another transaction can see all those rows. Well, that's an example of visibility. And when Postgres, and what's happening internally in Postgres is as you run that select statement, so when I say select star from users, it's actually going to be going through and looking at every single row, every single tuple in that page. And it's going to be running a little algorithm that looks something like this. So it's going to be looking, to see if the xmin, if that transaction was aborted. Obviously, we throw that row out. Or if it's in the future. So if the row was inserted by a transaction that started after we did, it's invisible. And otherwise, it's visible if the updating transaction, so the xmax, was aborted, or the xmax is behind us. So someone before us put that in. And
Sorry, is the XID generated chronologically?
yes, so this is one of the important things is that each transaction gets a sequential XID. So if I start a transaction, then you do, yours will be larger than mine. And if you're really interested in what's going on under the hood here, the method that Postgres uses to figure out if a transaction's aborted has a lot of really nifty optimizations and whatnot there. So you'll be able to go and take a look at that link. Anyway, let's get back to that initial question of what's going on. Why is count star so slow? And the reason is that at any given time in the database, there isn't one correct count star. The count star that you would see is going to be different from the one that I'll see, and there's no general purpose way that the database can keep track of that and can give you a faster, more correct number. So how are we doing for time? 5 minutes? Okay, awesome. So there's a couple of just little nifty things that I want to just quickly throw out there because this is stuff that I'm really into, and maybe hopefully this has kind of piqued some of your interests. So the first question is, what happens if two transactions try and delete the same row or update the same row? You'll remember that there's just that one XID, Xmax, and obviously we can't have two people updating at the same time. Well, the second one will always block, and this is actually a really important thing to know if you're dealing with databases and you're dealing with SQL databases, because that's super surprising. That's not a thing you expect. So for instance, if I try and delete a row and then you try and delete a row, you're just going to have to wait until I finish, and then you can go ahead with that delete. The second thing, and the astute amongst you might be thinking, well, those XIDs, those are just integers, and one of the problems with integers is they're only so big, and at some point they run out, and we have a random overflow.
Back to zero.
Yeah, back to zero, and then if you're curious what happens there, you can ask our good friends over at Sentry where they ran into exactly this issue. Specifically, what happens under the hood is as those numbers are getting bigger and bigger and bigger, there's a process internally called vacuuming. And what vacuuming in Postgres is a few different things. And one of the things that it does is it goes through and it basically cleans out the old transaction. So if we haven't used a transaction in a while, if it's not relevant, Postgres gets rid of that and then moves a pointer forward. So it says, okay, we can wrap around safely up until this point. But if you don't run that often enough, or you have a table that has a lot of inserts and a lot of updates, eventually you're going to start getting these warnings from your database. It says in I think it starts like 2 million or 3 million transactions, it's going to start warning you. And then if it gets too small, within 1 million transactions, the database is actually just going to hard shut down. It's not going to let you do any inserts or updates. And that could be a really big problem if you're running, say, at the scale of Sentry, where you're having probably millions of updates a day, because those tables are going to take probably about a week to go through and vacuum and clean out.
Is XID a 32-bit integer?
It's unsigned. So we get some wiggle room there. It's never been, I mean, chances are nobody in this room will ever run at the scale where it actually happens. But it is an important thing to keep in the back of your head. That's my talk. The last thing that I want to say is I'm hiring right now, so if you're if you're interested in education, if you would really like to work for a company where what you're doing day in and day out is making the lives of teachers happier and better, please, I'd love to chat with you. Yeah, let me know, come say hi afterwards. So, thank you very much for listening. Do we have time for questions?
Yeah.
Cool, any questions? Steve.
So one of the things you mentioned was that, you know, like for example, key value stores basically don't do transactional integrity because they're flat anyway.
Yeah.
But you said, you know, you can add your own layer to do that if you want. And it's always been my contention that I would rather do it in my layer than trust the database to do it for me for the kinds of transactions that I'm doing.
Yeah, so there are, like, it's a really good point. In some kinds of transactions, it can actually be a whole lot easier to implement them at the database at the application level as opposed to at the database level. So, like, the most common pattern, just to fill you in, if you haven't seen this before, to implement a transaction in a fundamentally non-transactional database, you essentially, like, let's say we're doing a bank transfer, you essentially copy the bank accounts to a new location with the new updated values, and then the final step of the logical transaction is to move a pointer. So we say we used to look at these bank accounts, now we're looking at these bank accounts. And that's one operation, and so the view of the world stays consistent all the way through. And it can be easier. In other situations, though, it can actually be incredibly complicated to get right, and it's really nice to have that implemented at the database level. So, yeah.
So the other part of this is race conditions, which databases all have when you've got multiple people accessing.
Yeah.
Or multiple processes. And my only solution to that is just have a single view.
Yeah, so that's definitely oftentimes what it comes down to. So if you ever find yourself in a place where you're trying to figure out blocks and stuff in your head, most likely the best thing to do is just forget all of it and do everything single file. One of the really cool things that, again, I wish I could talk about, I could probably talk for an hour about this, is Postgres isolation level. So what Postgres can do, it actually has a feature that lets you say, during my transaction, if any data that I've even looked at, so if I do a select start from users, if any user in that users table is updated, cause the whole transaction to fail and start it again, to guarantee for 100% certain that nothing can change while you're in the process of performing your operations. So it's really, really nifty. Anything else? Hey.
You know, if you can give this the amount of bits, like the size of the integer for these XIDs?
I actually know. You probably could recompile Postgres and like pick your value. You just have 64 bits, you know, a little bit of wiggle room there. But it's one of those things that in practice, like as long as you're running your regular maintenance, it's just not an issue, even at really high rate loads. Cool. Well, thank you all so much. I really appreciate your listening, and yeah, come chat with me afterwards.